Hello students, welcome back. The next topic is related rates, section 4. Here are the problems associated to related rates, and before starting any of those, please read through and appreciate the realistic nature of these problems. After all, one of the more important learning objectives for this course is empirical and quantitative skills. And indeed, they are empirical. Read through. So what do you think? Do you agree that these are empirical? Now don't be intimidated. In section 3, we already went through the structure of related rates problem. Here's an example. The problem gave you a relation between two variables, x and y. And it's typically implicit like this. Sometimes explicit. In that case, the problem is much easier than it appears, but most of the time it's implicit. And then we take the derivative implicitly with respect to the independent variable t. Then you're going to get the second equation like this. Equation number 1 and equation number 2. The first equation gives you the relation between two dependent variables, x and y, and those are dependent variables, so we can consider those as functions of the independent variable t, or the parameter. And then if you take the derivative implicitly by the chain rule, x prime and y prime pop up, and those are the instantaneous rate of change. So what do we have? We have the relation of rates. So relation of the variables and then the relation of the rates. So we have two relations. Consequently, we have two equations. But we have four unknown variables. X, y, x prime, and y prime. So normally this is not well-posed system. You cannot solve it. But sometimes the problem gives you, in this particular case, x equals 1 and y prime equals a negative 1. And in some cases, problems give you even more. In the end, after plugging all those in, you're going to get two equations and two unknown variables, and then you can solve it. That's the structure of the related rates problem. Keep that in your mind, and then let's begin 4.1. A snowball melts so that the surface area decreases at the rate of 1 square centimeters per minute. So this is a rate. Find the rate at which the radius decreases when the radius is 5 centimeters. I'm looking for the rate, but these are two different rates. And they're related. Now, how about the original? The surface area. And that decreases at this rate. And then we're going to find out the rate at which the radius decreases. And the radius is 5 centimeters now. The color coding will help. Now, through these, let's set up an equation. The surface area versus radius of a snowball. Remember the formula? S equals to 4 pi r squared. Remember this? By the way, the volume formula is 4/3 pi r cubed. But that's not the problem here. This problem has nothing to do with the volume, so this is not it. We want the surface area. So alright, we have this equation, and then let's take the derivative implicitly to find out the second equation. As a matter of fact, this is explicit equation, so it's pretty simple. Take the derivative, what do you get? Power comes out as coefficient, 8 pi r, and then r prime pops up. This one here, r prime, is the rate that we want to find out. And then this one here, s prime, this one we know. It decreases at the rate of 1 square centimeters per minute. And the radius, what's the radius? Radius is 5 centimeters at this moment. So that's the radius. And then that's the surface area now. Okay, the color codings are all done. Let's see. I'll be bigger font. Yeah, we have all those different colors, so a little bit bigger font will be helpful. Now we have 4 known variables, s, r, s prime, and r prime, but the problem gave you r is 5 and s prime is 1, or actually it's decreasing, so it's -1. So we can go down to just 2 equations with 2 unknowns. As a matter of fact, it's even simpler than that. So r is 5, so okay, that's 5. And then s prime is decreasing by 1. So let's put -1 there. If you don't want -1, just go ahead with 1, that's fine. But me personally, it's decreasing. So I'd like to put negative there. You don't have to use that. You can just calculate and then you can say it decreases blah blah blah. Okay, alright. And then r is 5, so okay, that's 5. And then r prime, okay, that's the quantity you want to find out. And of course, you can find out s as well, even though this problem did not ask you. Well, let's go ahead and do that anyway. I could have certainly written a problem a little bit differently and slipped in to find out the surface area at the time as well. I mean, when the radius is 5. So let's go ahead and do that. Multiply 5 squared, that's 25 times 4. So this is what? 100 pi. And then that's going to be what? Pi is about 3.14, so 314 approximately speaking. Yeah, I don't even need a calculator for that. Approximately speaking. Never mind, just 314 will do. Now, how about r prime? That's the problem. That's the main body of the problem. Let's see, let's divide everything away. Then you're gonna get r prime equals to -1 over, let's see, 8 times 5, 40 pi. And then this one, I need a calculator. Let's calculate this. Well, that's what I'm getting. So approximately -0.008. Okay, that's the answer here. The problem did not ask you the surface area at the time, but if it does ask you that, then you can answer it too. And this problem did not specify how many decimal digits to take, so or it didn't really ask you anything about taking a decimal value at all, so maybe you should be able to answer like this, 1 over 40 pi, and then walk away. Anyway, that's how you can handle this problem. This is one of the most one of the simplest type of problem, because the original equation there is not implicit, it's explicit. S is given as a function explicitly, so it's easy. And then we didn't have to worry about the first problem at all. We did it anyway though. But in other problems, you'll see situations that all these variables are intertwined. Let's see, what did I do in my answer key here? Okay, start from the relation between the surface area and the radius. Derivative, so second equation. Plug in the numbers, S prime and then R. And then plug in, you can find out S, even though that's not the core part of the problem. The core part is this. So this is 5 centimeters here. And 5 times 8 is 40, so divide away. So we have -1/40 pi centimeters per minute. Okay, so if this problem asks you not the centimeters per minute, but if it gave me say millimeters per minute, then you have to move this dot one more. It can be a bit cumbersome to calculate with all those units, but if you can, that can be useful because units tell you what the final answer should be or whether you should be multiplying or dividing. So we want centimeter per minute. Okay, there goes the solution. Now, do we have enough time for another problem here? Maybe not. We'll stop here and then let's cover the other two problems in a separate video.